Good morning, everyone. My name is Luengo, David. Um, I come from Universidad Politécnica de Madrid, or Madrid Technical University. We are the largest technical university in Spain. We only teach engineering degrees, and we have all kind of engineering degrees, from industrial engineering, electrical engineering, civil engineering, aeronautical engineering, biomedical engineering. So we have all kind of computer science, also all kind of engineering degrees that you can think of. Probably we have a degree on that. Okay. So we are based in Madrid, and we have three main campuses around Madrid. One is in the city center. That's the main campus. Then we have another campus which is located west of Madrid, where the main facility there is our computer science faculty, and then also we have a large software center and a large biomedical research center over there. And finally we have the South Campus, where we have also computer science, electrical engineering, and topography, and that's where I am based. We have been collaborating with Zaporizhzhia for the last 3 years through one project that we have. You can see the logo here. It's the BioArt project. It was funded by the Erasmus Plus program from the European Union, and essentially in this project, maybe I should put this in full screen mode. Okay, 1 second. Yes. So in this project, essentially we are trying to develop new bachelor and master curricula, both in Ukraine and in Israel. So we have 4 higher education institutions in Ukraine where these degrees are being developed. So we have Vinnytsia National Technical University, we have Priazovsky State Technical University, we have Donbass State Engineering Academy, and then Zaporizhzhia National Technical University. Sorry, I cannot remember the new name, Galina. Sorry, sorry about that. So in those 4 degrees, some of the new bachelor and master courses that you have starting last year, and some starting last year, some others starting this year, have been developed throughout this project. And we also have other 3 higher education institutions in Israel, where we are also developing new master and bachelor courses. They are Shamoun College of Engineering, Bar Ilan University, and Olon Institute of Technology. Okay. Besides that, we also have an agreement, an Erasmus Plus agreement with Zaporizhzhia National Technical University to exchange students and professors. I know that in the current situation, exchanging students and professors can be difficult, but we've already had 4 Ukrainian students who have come to Madrid during the last academic year, and a couple of Spanish students who went to Zaporizhzhia during the last year. I have been there also, and Galina came here to Madrid. Well, Galina and other Ukrainian professors came here to Madrid. So this agreement is still active. So I hope some of you will come to Madrid at some point during this academic year. And now I think it's time to start. As I said, this talk is given in the context of this project, of this BioArt project, where we want to develop new bioengineering courses. And this talk was actually developed in the BioArt project, and it was given. This is the third time I'm going to give this talk with modifications. It was originally given in Israel at the beginning of the year, then in the International Days of KU Leuven in Belgium, and now here in the Zaporizhzhia International Day. So thanks, Galina, for inviting me to give this talk. The schedule for the talk, my plan is to give like maybe now 1 hour, 10-minute talk, then have a break, like a 20-minute break, and then finally the second hour, okay? Because I think 2 hours and a half without a break in the middle is just too much. Okay, so what am I going to be talking about today? I'm going to be talking first about biometric recognition. Maybe some of you already know what biometric recognition is, but in any case, I will start from scratch, from the basics, just defining what is biometric recognition, the main challenge and the main approaches that we may find in biometric recognition, and then I'm going to focus on ECG-based biometric recognition. Okay, so the idea is to talk about how we can identify individuals through their heartbeats, recorded by the electrocardiogram. And since I am a signal processing and machine learning guy, I'm going to focus on the signal processing and machine learning algorithms that are used or that can be used to perform this recognition. This is rather than a research talk. This is going to be more or less an educational talk. So I'm going to focus. My presentation is going to be focused on the two approaches that were implemented by two bachelor students of mine, so that you have an idea of what can be done with the tools that you will learn in your curriculum. Okay, so as I said, these were two students of mine. Their final year project for the bachelor's degree was implementing two different biometric recognition systems from scratch. Okay, they started from with nothing, and they were able to implement a full system in MATLAB and to test it on real signals, and with very good results actually. Okay, so let's start. This is the plan for the talk. First, as I said, I'm going to start from the basics, just introducing what is biometric recognition, what is ECG-based biometric recognition, and why the ECG signal is a good candidate to identify people. Then I'm going to talk about two approaches, two of the main approaches, the main classes of biometric recognition systems that we may have. One is fiducial methods. In fiducial methods, essentially, we extract a set of fiducial points, a set of key points from the signals, and we use those key points to perform the recognition. And on the other hand, we may have non-fiducial methods where we do not need to extract those points. We just take a block of the signal and we perform some transformation on that block to extract features that will be used to perform the recognition in the end. Okay, in both cases, I just specified the structure for fiducial recognition because the non-fiducial one is essentially the same. Okay, so we will see the block diagram of the proposed approach. As I said before, each of these methods, the fiducial and the non-fiducial, correspond to one final year project of one student of mine. So we will see the block diagram. In the case of the fiducial method, the pre-processing and fiducial point extraction. Then we end up with too many features, and we have to perform some dimensionality reduction. We have to select which features we are going to use for the classifier, the classification to distinguish the different individuals, and some results using a public database. Same approach for the non-fiducial one. Here, instead of fiducial point extraction, we will see which is the pre-processing required to extract the features. Okay, and we will also perform dimensionality reduction. And then after presenting these two projects very briefly, I would like to give you an overview of some of the more modern approaches that people are using, and how deep learning methods, which are like state-of-the-art methods in machine learning, how they are being used, or they have been people have started using them recently for ECG biometrics, and then some conclusions and future lines. Okay. So let's start. What is biometric recognition, or what is biometrics? Okay. At the beginning of the past century, biometrics referred to obtaining some biometric data and some data related to the biology of a person, usually just for healthcare purposes. Okay. More recently, the term biometrics have been associated to individual recognition. Individual recognition can actually be based on three main things. Okay. First of all, individual recognition can be based on what the person knows. So some kind of secret information that only the individual that needs to identify himself or herself knows. For instance, this can be a password or a cryptographic key. When you enter your email system or your university services, or the Moodle of your university, you do type in a password, and that password identifies you as the user of the system. Okay. Or if you have like a driving license or some kind of or your passport and you are using that to access that number, okay, to access some online service, then that's some secret information that, well, you are supposed to be the only one who knows it, and then you can identify yourselves with that number. Of course, this is you can see the main disadvantage, the main drawback of this method immediately. If you handle the password to some colleague, or if someone finds out which is your password in some way, then they can easily supplant your identity. Okay, someone can easily access some system pretending to be someone who that person is not. Okay. Then the second possibility is, okay, instead of secret information, we are going to use some token, some physical device that only the person has. This can be a passport or a personal ID card, some physical key, like the keys of the car, or the keys of your house or your office. Okay. Then if you don't have that token, you cannot access your office. You cannot open the car. You cannot, if you have it with the passport, if you don't have a passport, you cannot access a foreign country, for instance. Okay. Of course, this also has problems, because tokens, physical devices, can be stolen or can be lost. Okay, and they can also be falsified. Passports can be falsified, for instance, or keys can be duplicated. So it also has problems. Recently, this kind of token approach is being enhanced by mobile phones. Okay, maybe you have your mobile phone, and inside your mobile phone, you have an app that allows you to identify yourself and to access certain services, or even to pay online, for instance. Okay, online or physically. Sorry. And then there is a third possibility, which is the one that we are interested in, which is identifying someone by some intrinsic feature of that person. And this is what we call biometry. And here you have some examples of biometry or biometric recognition. You can identify someone, for instance, for the fingerprint, through the fingerprints. that's probably the most widely used biometric recognition nowadays. You can also use the iris. You can use the shape of the hand, or something which is becoming now very popular with mobile phones, by using some kind of face recognition. This has advantages with respect to the previous two approaches, because if you use your fingerprints, your iris, your face to be recognized, that's something that can, well, sometimes it can be falsified, okay, wherein people have been able to full face recognition systems wearing a mask, for instance, and there are templates that can be used to falsify fingerprints, but some others can be more difficult to falsify. Some others, like the iris or the ECG signal that we will see, are more difficult to falsify. And also, this is something that you cannot forget, as it could happen with secret info, and you cannot lose, and it cannot be stolen from you. Well, usually a finger is something that they are not going to steal from you. And if they do, then that's not the biggest of your problems, okay? Having someone identify as yourself is probably not the biggest of your problems if you lose a finger or a hand. In any case, this is something that is increasingly being used to identify people, okay? Well, actually, I didn't say it from the beginning, but I will keep talking all the time, essentially. So if you have some question, you can interrupt me at any time. Okay, if you have questions, doubts, curiosities, just feel free to ask at any time. Okay. So here you have a definition of biometry taken from this book, which I highly recommend as an introduction to biometrics. It's already a bit old because things here are progressing very, very fast. So some of the systems and some of the conclusions that are taken in this book are not valid anymore. But as a first introduction to biometrics, I think it's a very nice introduction. Okay, so what is biometry? Essentially, biometry is the science of establishing the identity of some person, of some individual, based on some kind of, I said before, physical, but can also be behavioral characteristics. The way a person walks can also be used to identify that person. Okay, and this has to be done nowadays either in a fully automated or semi-automated manner. So it has to be done using digital means and some kind of microprocessor or computer. Okay. The advantages I already mentioned before. It's difficult to manipulate or to share. You cannot share your fingerprints, or to forge. It's much more difficult than passwords. Although, of course, once this kind of things are being used, then people are finding ways to falsify them, but it's still more difficult than traditional identification means. This is something very important that I did not mention before. We can, with biometric identification, we can avoid false repudiation claims and multiple enrollments. So if you're using your fingerprints or your iris to access some facility, you cannot use it multiple times. If someone else has a fake fingerprint or a fake iris and tries to enroll, the system is going to say no. It is impossible. I mean, there are no two fingerprints which are equal in theory. I can and also. You cannot claim that you did not access the facilities. It's much more difficult to claim that because you used your fingerprint, and the fingerprints are supposed to be unique, okay, and difficult to falsify. So as an anecdote, I can give you one example. I don't know if things work the same in Ukraine, but in Spain, I can give you one example of a guy in my hometown, a guy who was caught speeding in the highway. He was going with a motorbike, at 240 kilometers per hour, and the limit was 80. Okay, so it was like 3 times the limit. It was highly above the limit. Of course, as a fixed radar caught him, but they could not. They just saw the plate, the number of the plate license. So when the fine went to his home, and then they asked to identify who was the person driving the motorbike, and this was a guy, a 20-something-year-old guy, but he lived with his grandfather, and his grandfather also had a motorbike license. Of course, he was in the 90s. He had not driven for a long time, but then he said, no, my grandfather was driving. Okay, so and there was no way they could say that it was that was not true. So in the end, he had to pay the fine. But in Spain, we have a driving license with points, and for that offense, he would have lost his driving license. Since it was the grandfather who was driving, then the grandfather lost his driving license, and not the grandson. Okay, so this could be avoided if we could implement biometric recognition. This could be avoided, because then we could say for sure that it was not the grandfather who was driving the motorbike. Okay. Also, one important thing for biometric recognition is that some traits can be used as a proof of life. This means that if you are using iris recognition, or if you are using ECG-based recognition, in order to get the ECG signal, the person has to be alive. And that can be important in some contexts. And finally, biometric traits can be combined either with traditional traits, or with other biometric traits, obtaining something which is called multi-biometry. So we could use a combination of iris, ECG, and fingerprints, for instance, to provide enhanced reliability. That is about the advantages. Of course, all these methods also have some disadvantages. The main disadvantage is that this is still starting. Okay, some biometric systems like fingerprints have been used for a long time, so we know how they work. We know how to make them work, and which are the limits and the things that work well and do not work so well. Face and iris recognition have received a lot of attention in the latest year, and they are also working quite well right now. There are commercial systems exploiting this kind of biometric recognition features, but others like ECG-based recognition, they are just starting. ECG-based recognition, we will see later, it started like 20 years ago, but as far as I know, there is still no commercial system which is using ECG-based recognition, and there is not a well-established method which can be considered like the de facto standard for ECG-based recognition. Okay. Also, we have to be careful about issues like inter or intra-individual variability. So there are some people who could share the same biometric traits, like twins. Twins could share biometric traits. So could maybe in that cases like facial recognition would not be enough to identify those people. Also, traits can change with age. This is a problem. For instance, with ECG-based recognition, there are, as far as I know, there are no serious studies that establish how the ECG signal changed with time. Okay, and also sometimes the acquisition of the signal, if we get a signal, a low quality signal, it may be impossible to identify someone. Okay, here you have some of the problems that we face when performing biometric recognition. So the first one is with fingerprints. You could have this is a good fingerprint. Okay, it's more or less properly located within the acquired sample, and the whole fingerprint is acquired. This is an example of a problem where the fingerprint is rotated. Okay, so we can have problems with trait orientation. Of course, this nowadays we can more or less easily take this into account, because we could either extract features which are invariant to rotation, or we could try to find the axis along which this fingerprint is oriented and rotate the image. This is more serious problem, because this is an example of an incomplete trait. You can see here that the top of the fingerprint is missing. If this top of the fingerprint is missing, this means that we might not be able to extract the features that we need to recognize the person, or even if we are able to extract those features, we could be making mistakes. So, okay. Here you have another example of orientation. If we have a good image like this one, clearly we would not have any problem in recognizing this person, because the lighting is appropriate and the person is looking directly towards the camera. But if we have this image rotated, image recognition systems today might have problems. In this case, we might still be able to recognize the individual in this case, unless we have stored also an image from the guy looking in front and looking to the side. If we have that image stored in memory, we might probably be able to recognize the person. If we only have this image, probably the system will not be able to recognize the person. Okay, and here you have an example with light conditions where we have good lighting. Here we have some shadows that might also be causing problems. Okay. Well, other problems are individual variability. If so, here that's not shown here, but for instance, if we acquire an image of this guy like that, and then he takes off his glasses, or if his image is not wearing glasses and then he puts on glasses, believe it or not, but image recognition systems might have problems. I don't know if you have used these automatic systems that they have in some airports, where they can grant you access just with the passport and with the with a camera. And so they are using face recognition to grant access into some countries with your passport. Well, whenever I use those systems, I always have to remove my glasses, because otherwise the system does not recognize me. Okay, so of course those things will probably improve as technology improves, but nowadays they are still an issue. Okay, here you have an overview of some of the main biometric traits that are being used today. Okay, you have fingerprints. Here you have an examples. You have palm print. Okay, so this is the lines of the hand. They can be used also to recognize people, not just to predict the future. Okay, the hand geometry. Here you have the face recognition, widely used by mobile phones nowadays. Iris recognition, which is more robust and more difficult to falsify than face recognition. The electrocardiogram, which is still not a very well established signal, but which is gaining more and more attention. And then some behavioral traits. As I said, we can recognize someone not just because of his physical traits, but also by how he behaves. And one typical behavioral trait is the gait, the way some person walks, and this is something that human beings do all the time. Okay, probably you have had this feeling where you see some friend or some relative, you see him or her 30 meters away, you can still not recognize that person for his face, but you can recognize that person for the way he or she walks. That's gait recognition. We also directed a bachelor project a couple of years ago about this. I'm not showing you that because the results were not so good as we expected. Okay, but there are some approaches which are doing this. Signature is another classical identification trait, and signature is not something intrinsic of the person. It's something which the person has adopted himself or herself, okay, and which can be changed. You can change signature over time, okay, but at a given time slot, your signature is able to identify yourself. Also, some people, some studies have been made about keystroke pattern in computers. Turns out that the keystroke pattern, the strength and the rhythm that we use to strike keys in a keyboard when we type is characteristic of each one. The voice is also characteristic of each person. So there are many biometric traits that can be used, and we will not explore that, but they can be used either in a standalone mode or combined in multi-biometric ways. Any questions so far? No? Okay, so we will continue. Here you have a block diagram of a typical biometric recognition system. So we have a user who wants to enter the system. Okay, so we have essentially two stages. First of all, if this is a new user, the user has to enroll the system, which means that we have to acquire some representative biometric traits from that user, which will be stored by the system and then used to decide whether that person is who he or she claims to be or not. So essentially, we will have some biometric interface where we will ask, we will have a sensor, and we will ask that person to provide his biometric trait. So for a mobile phone, it could be typically nowadays, there are two systems which are being widely used. One is face recognition, and the other is fingerprint recognition. So we could ask the person to identify herself either by having, okay, so I have here my mobile phone. So we will, okay, so we will either ask the person to put his mobile phone apart and to take a picture of himself or herself with enough distance so that the whole face can be taken, or we could use, I don't know if you can see it properly. So in my case, I have a fingerprint recognition. So I have here a sensor that, first of all, has to be trained. So you have to put your finger there, and it has to, the system, the mobile phone has to acquire the fingerprint, and then I will be able to unlock my mobile phone using my fingerprint. Okay. So that's the first stage, enrollment. So we will have a user, a sensor, we will acquire some trait, we will perform quality estimation, and if the quality of the trait, of the acquired trait, is not good enough, we will ask the person to repeat the process. Okay, so if you take a picture of yourself with the mobile phone, and then the part of your face is not properly seen, or the lighting conditions are not good, the system will ask you to take again the sample. After acquiring the sample, we will provide some enhancements, some processing, some pre-processing to improve the quality and to remove noise. Okay, I don't know. Oh, okay, thanks, Galina. Yeah, you can write the questions in the chat. I will try to look at the chat from time to time.
That's why I want to tell everybody that I'm controlling chat, and if they want to ask you a question, they could even write it in Russian, and I will translate it to you. Okay. Russian, yes. Ukrainian, so any comfortable language. Okay.
German, Galina?
No, German is for me impossible. Probably someone could translate also.
Spanish, even. Okay. Anyway, so we will perform some enhancements and some signal processing to improve the quality, to remove noise, and from that we will extract the features which will be used to. Okay, is there house scanners? No, Sorry, I will not explain how scanner works because that's not my field. Okay, so I'm not working on how to acquire that signal first of all. So I'm a signal processing machine learning guy, and also we will not be talking about face recognition or about fingerprint recognition. We'll be talking about ECG based recognition. So now I'm trying to give you a broad overview of biometric recognition systems, but I'm not an expert in fingerprint or face recognition. Okay. Well, in any case, we will extract the features and we will store those features. This is important because usually, in most cases or in all cases, I know the whole feature is the whole signal which is acquired is not stored. Okay, we're not going to store the whole fingerprint or the whole image. We're going to extract some features, some characteristics from that signal that we have acquired, and that's what we are going to store in our database. And then that template database is going to be used to identify the person. And here we have two main approaches, as I said in the beginning. One is fiducial approaches, where we extract key points from the signal, and we use those key points. Those key points are the ones which are stored in the database, okay, or some features which are extracted from those key points. Like for instance, in the case of the ECG, it's time differences and amplitude differences, okay, or non-fiducial approaches where we perform some transformation of the signal regardless of those fiducial points. So we don't need to identify those fiducial points. We just perform transformation of the signals, and from that transformation we extract features. You will see this more clearly when we see the two approaches that I'm going to talk about. And then that's the first process, enrollment. Then the second process, recognition, works exactly in the same way. The user who has already enrolled the system, we already have his features stored in the database. So we have this feature who wants to enroll the system, to enter the system again after some time. So we acquire the biometric trait, we perform quality estimation. If the quality is good, we perform signal processing to improve the quality, and we extract the features. And what we do is we recover the features from the template database and we compare them to the features. This is a pattern matching problem. We compare those features to the ones that we have extracted from the new user that wants to enter the system. And here we have two possibilities. One is authentication, which is the simplest case. In this case, the user says, who tries to enter the system, says his or her claimed identity. So I say, okay, I'm David. Let me get in. And then the system just needs to check the template that is stored from me and compare it to the new template. If the match score is high enough, here there will be a threshold, okay, a matching threshold. If the matching score is high enough, then access is granted. Otherwise, access is denied. The more challenging problem is not authentication, is identification. Because in identification, I have a new user, but I still don't know who this user is. And I have to identify that user. So I have to do the same as before, but checking all the templates that I have in the database. So it's a very similar process, but it's not checking just one. It's checking many users, okay? Here you have essentially what I have told you. So you have the enrollment where, so here we are working with fingerprints. The fingerprint is acquired. You can see that often the quality is not the best one. So we perform some enhancement of the fingerprint, okay, to get the best possible quality. We extract the features. From those features, we construct a template and we store that template in the database. For verification or for authentication, we do the same, extract the fingerprint, perform image enhancement, and then we compare that template that we have extracted from the new biometric trait with the one that we have stored and that we search in the database using the claimed identity from the person. So we just have to perform one comparison. We perform that comparison. We go to the decision rule. If the similarity is large enough, then we grant access. If it is not, then we deny access. And one thing that we can always do, and which is always good to do, is updating the template. So if we decide that the person is who he or she claims to be, we should update the template. And there are several strategies. Okay, the easiest one is we could just replace the template. The old template, sorry, could be replaced by the new one. But we could also perform some kind of adaptive biometric system, where this template is gradually adapted every time the user enters the system. And finally, the last possibility is identification, which is like this one, but without the claimed identity. So I have the new trait, quality improvement. I extract a pattern, a template, okay, and then I check with all the templates that I have stored in the database. I perform some pattern recognition, some pattern matching, and then I send those scores to the decision rule. And essentially, here I will select the one that has the largest score. Usually here I will also set a threshold, because if the score for all the patterns is very low, then there is a chance that this user will not be registered in the system. And then I should say, no, you are not registered. You have to perform enrollment before you can use the system. Okay, well, that has been like a general description of biometric recognition systems, and now let's start with the ECG. So, okay, is there some? Okay, no. Okay, well, so what is the ECG? Probably you all know. The ECG, the electrocardiogram, is the main signal which is used to record the activity of the heart. Essentially, you have here a picture of the electrocardiogram. So essentially, the electrocardiogram is a quasi-periodic or largely repetitive waveform, which is composed of some characteristic waveforms. The main waveform that you will find in the ECG is what we call the QRS complex. The QRS complex is ideally composed of three peaks. One small deflection, the Q peak, then the largest deflection in the electrocardiogram, the R peak, which marks the occurrence of a heartbeat, and then the S peak, which is another negative deflection. Some of these peaks may be missing, but we still call that a QRS complex, okay? So this might not be present, or this might not be present. So we could have just like two waveforms, these two or these two. Okay, those things happen, or it could even be inverted. We could have the wrong polarity, but in the end, we have a large peak, and then we have some isometric segments. Isometric segments are segments where the signal should be equal to zero. Should be following the baseline, the isometric line. Okay, so we have these segments, PR segment, ST segments, and we have two other main forms: the P waveform and the T waveform. These P waveforms is caused by atrial depolarization. The electrical cycle of the heart starts in the atria and then propagates to the ventricles. So this is atrial depolarization, this is a ventricle depolarization, and this is ventricle repolarization. Atrial repolarization occurs at the same time that the QRS complex, but it has a much lower amplitude, so we will not see it. So this is what we have. Okay, we have these waveforms. We can have other small waveforms, but essentially these are the main waveforms that we have. Of course, what I'm showing here is a very clean signal. In fact, this signal is going to be corrupted by noise and interferences. We're going to have baseline wonder, electron motion, moving artifacts, power line interference, etc. Okay, and this is the signal that we have to work with. So the key question is, can we use this signal to identify people, to identify individuals in a unique way? And the answer is yes, because when we plot this signal, we use this kind of plot, okay? And when you look at ECGs, they all look similar. But in fact, there are changes in the morphology of the QRS complexes, in the morphology of the P and the T waveforms, and also there are changes in the duration and in the amplitudes of these waveforms. And those changes in the amplitude and the duration depend on physical characteristics of the person. Okay? So for instance, the heart size. The heart of each person has a different size, has a different morphology, and has a different orientation. The heart can be more or less rotated inside the body of a person. Also, the conduction velocity of the electrical signal inside the heart is going to be different for different people. Okay, and this means that these waveforms that we are seeing in this figure could be shorter or longer. Okay, and also there are some people who have pathologies, and if those people have pathologies, this is going to be reflected in the shape of the ECG. Well, some advantages of the ECG as a biometric trait is that it can be used as a proof of life. Okay, I already mentioned that before. Nowadays, it's difficult to counterfeit. In fact, as far as I know, it's not possible to counterfeit. Okay, it's not possible to or it's not easy to generate a fake ECG signal to mislead a biometric system, and it is unique for each subject. Okay, this is based on what I just said, because the heart size, the conduction velocity, the orientation of the heart is unique for each person. Those are the advantages. There are also some disadvantages, and then what some researchers are doing in the last few years are trying to reduce the disadvantages and to check whether this can be used for biometric identification. So first of all, one practical disadvantage is that ECG acquisition is still cumbersome, although this is improving. Okay, the traditional way of acquiring the ECG requires 3 electrodes. So you place like 2 electrodes, and then you have to place one electrode in a neutral, in an electrical free part. Okay. Of course, if we are going to use this, for instance, to unlock our mobile phones, then we don't want to do that. But nowadays already there are approaches to do that. If you have for instance, if you have an iWatch, okay, or an Apple Watch, that Apple Watch, the latest versions, they are able to acquire the ECG. How do they do it? Well, they just have one electrode in the watch. Okay, I don't have one; I have regular one. So they have an electrode in the watch, which is directly in contact with your skin, and they have like a wheel on the side, and then when you touch the wheel, then it is able to record your ECG. Okay. So this is one approach that could be used to acquire ECG for use as biometric identification in practice. So this is something which is still a disadvantage, or could be still a disadvantage compared to other biometric approaches, but I don't think this will be a big problem in the future. Okay, this may be more critical. The ECG can change with age and with the physical condition of the subject. If we gain or lose weight, the signal will not be exactly the same. As we get old, our ECG signal will change. However, you may think, okay, then this is not a valid trait. Well, that's not so clear, okay? Because so on the one hand, we can have adaptive biometric systems, okay? We have we could have systems which update the pattern and the template which is stored, and they can adapt it as well as the user enters the systems again and again, so we can adapt the signal. If if the signal is changing slowly, then we will have no problem. Or if we are able to extract traits which do not depend on the morphology or which are robust with respect to those chains, then we'll have no problem with this change. As far as I know, there is no serious study which addresses this issue. We will need to have signals acquired on the same subject for a long time, or with change in the physical condition of the subject. And as far as I know, this has not been done. Sorry, or at least it's not public. So there is someone. Oh, yes, but I cannot understand the question.
Yes, there is question. Can you hear me?
Yes.
So I will try to translate it. If when you was making state of art, have you considered the unique picture of blood? I'm looking for the word also. Sorry, quickly.
Sorry, Kalina.
One moment.
Okay.
For the wine, yes. Have you taken in account the picture of the vines on the hands as one of the variants of identification?
I don't understand that word.
The tubes where blood is functioning in the body.
The veins. The veins.
Yes, veins. It's
okay. Well, that's interesting. I had never actually thought about that. Okay, I can tell you that there are some approaches. I have seen one multibiometric approach where the ECG is combined with blood pressure to identify individuals. And clearly, if we are talking about blood pressure, we need to consider veins configuration. Let's say for the ECG, I don't think that should be. Of course, it could affect the outcome maybe, but take into account that here the ECG does not measure. It's not a pressure signal. Okay, it measures the electrical propagation of the signals inside the heart, and in principle, that's not related to the veins or to the blood pressure. So I don't think it's an issue, and I don't think it's related if we just consider the ECG. Okay, if we consider the ECG combined with other biometric measures, it should be taken into account. Yes. That's a good question.
So maybe read for everyone. Yes. So what types?
Yes,
there's one more question. What are types of individual recognition that have not been studied sufficiently, but may appear in nearest future and become popular?
Well, I have seen many kind of biometric recognition systems which are based on all kind of biomedical signals. Okay, so for instance, I remember seeing maybe a couple of years ago one system which tried to use the electroencephalographic signal, the EEG. They claimed that they got good results. I'm a bit skeptical about that, okay, because that signal changed a lot with the mental activity of the subject. But who knows? Maybe at some point the mental activity of a person can be used to recognize the person. Other things like I just mentioned blood pressure or photoplethysmography. Photoplethysmography is used in intelligent watches nowadays, and it can be used. I had a Ukrainian student working on that last academic year. It can be used to estimate the heart rate and the photoplethysmographic signal, which is I don't know if you go to the doctor and they measure the amount of oxygen concentration in your blood, they use photoplethysmography. So essentially, there is a light ray, a ray of light, sorry, which is sent through the skin, and the reflection is able to give you information on blood pressure and the blood flowing through your veins. Okay, and then you have a signal which is quasi-periodic and which might be unique for each person. I'm not 100% sure that could be used to identify people, but it could be used as a factor. So in general, there are many approaches and many signals that could be used. There is also a question about whether, for instance, small traits which could not be used alone to identify one individual, whether this could be combined or whether they could be combined to identify someone. I think that's one of the challenges for the future, and that's one of the things I believe which are very interesting for the future. Not just using one biometric trait, combining many biometric traits, and if possible, combining biometric traits which could not be used alone to identify some person, and biometric traits that could be acquired with a mobile phone or with an intelligent watch. Okay, like small features, photoplethysmography, I just mentioned, blood pressure, also the ECG. Okay, even electrodermal activity, for instance, electrodermal activity is related to the sweat, and of course you say, well, we all sweat, but and it depends a lot on the condition, but could be another factor that all alone, I'm pretty sure it will not be able to identify anyone, but all together with other information could be useful. Also, the accelerometers in the that we have in intelligent watches or in mobile phones. Okay, we have accelerometers which can be used to see the behavior of the people, the gait. For instance, that's the information we used in the project that I mentioned before, where we were trying to identify people from the gait. We used the accelerometer in the mobile phone, which was the person was wearing in his pocket, to try to identify the person. And all alone, that did not work so well as we expected. But maybe combined with other traits, that could have good results. So my answer would be, in short, okay, in one sentence, there are many traits that could be used. I don't think that a single trait will be able to identify everyone with enough reliability. So my guess for the future is that we will see more and more multi-biometric systems, where several traits that on their own might not be enough to identify people. When combined, we could obtain systems which are more and more robust. So I don't know if I answered the question or I answered something else, but that would be my answer. Okay, many different features can be used, and the future, I think, lies in combining those features. Okay.
Thank you very much. Yes, I suppose no more comments since you answered.
Okay. Last issue, which may prevent the use of the widespread use of ECG based biometry is privacy concerns. When you use your facial image or your fingerprint to identify yourself, you're not disclosing any information about your health status. However, when you are using your ECG signal to identify yourself, some pathology, some cardiac pathology may be exposed. So people, some people who are critical of ECG as a biometric trait are saying, okay, we cannot give this information to big companies to identify people, because then they will use it to screen people who have cardiac pathologies, and they will use that to fire those people. So there are privacy concerns which occur here that do not appear in other biometric identification systems. Okay, and that we have to take into account. Here, I'm just going to give you, before moving to the two main systems that I want to describe. Here, I want to give you just a very brief overview of some of the key systems that have been developed well throughout the last 20 years. So the first application of ECG-based identification occurred around the year 2000. It was proposed by Lena Biel in Germany, or from Germany, in 1999, and then well, that was the conference paper, and in 2001 they published a longer journal paper, and that's people starting thinking of the ECG as a way to identify people. Okay, so well, they used a fiducial approach where they extracted features from the 30 features based on waveform durations and amplitudes from the ECG. They used PCA, which is a very well-known machine learning method to perform feature selection and dimensionality reduction, and then one machine learning approach to perform classification. It was tested on a small set of subjects, just 29, and they claimed that they obtained very, very good accuracy. Unfortunately, they used a private data set, so it cannot be, we cannot check their performance, okay? Of course, this system was still the first one, so they were the first to propose this, so that has a lot of merit, but it was not the best possible system. Soon after, Stephen Israel proposed, well, in the United States, proposed an approach which used a single electrode, 15 features, normalized times. Since then, these features have been kind of become a de facto standard. Okay, so many other approaches do different things. They do different things for dimensionality reduction. They do different things for classification, but they use the same set of features. And essentially, it's just normalized times. It's differences between the occurrence times of different waveforms. So, for instance, the occurrence of the Q waveform to the R waveform, the time from the R peak to the S peak, the duration of the P waveform, the duration of the T waveform, that kind of information was used. They use a stepwise feature selection approach, and then linear discriminant analysis for classification. They tested that on 29 subjects across 41 sessions. They were changing the parameters, okay, like the number of features they used for the classification, and they claimed that they were able to attain up to 100% accuracy. Of course, their data set was private again, and the number of subjects was not very, very large. As far as I know, the first ones who proposed a non-fiducial approach were Plataniotis et al. In Greece, and they and then that approach was extended in 2008, and they use a non-fiducial approach based on autocorrelation. We will see that, because essentially my students, one of them implemented this method, okay? Well, an improved version of this method, because we improved some parts, but essentially it was this approach. And then the other ones implemented an extended version of this approach. Okay, so the first one used this approach with amplitude features extended that were proposed in this approach. Okay, that's also why I'm giving you this overview. Okay, so the other one implemented this approach. Essentially, they took segments of the signal, they performed autocorrelation, they perform dimensionality reduction, and then classification using linear discriminant analysis. Okay, this is from a computational point of view, this is much less demanding and more robust, because in this case we have to identify the features, the fiducial points. Okay, and finding the R peaks in the ECG is very easy, and it works very well. But finding the beginning and the end of the P waveform, the beginning and the end of the T waveform, when we have noisy signals, is not so easy. We can make mistakes, and then we can have cases where those samples cannot even be identified. And if we cannot identify those samples, then we cannot apply this approach. Okay. Well, as I said, in this case, it's the same approach as in 2005, but if you see, the number of features has been extended. From 15 time features, we have moved to 21 features, which include not only times, but also amplitudes. And as we will see in the approach that I'm going to show you, this is going to improve the accuracy quite a lot, in fact. Okay, those are the basic methods that people started working on at the beginning. Since then, there have been many and many approaches, so I didn't want to put many slides for showing all these approaches. So what I did here, what I put here, is just 3 reviews, 3 more or less recent reviews, where they where they perform a survey of different biometric recognition approaches. So if you're interested in this topic, the way to start, well, I always recommend to start with the classical, with the first works, because they provide a lot of insights and they are easier to understand for students. Okay. But if you are interested in doing research in this area, you should probably start with some of these recent reviews to see which is the state of the art. Okay. In any case, I don't know how we are doing. So I don't know. Maybe we could make a short break now, and then what time is it? And then I will show you the 2 approaches. Is that fine, Galina?
For me, it's fine. Maybe some questions.
Yeah, if there are questions, of course, I can answer them now. If not, I will just make a short break now, and then we will see both approaches, because I prefer to see first one and then the other, and then you can see the differences, how both work. Okay, and then if we have time, we will go through the deep learning. If not, we can skip that. In any case, I will, Galina, I will send you the slides so that you can share them with the students. That's perfectly fine. Any questions now?
So, as no any questions now, I suppose we could start small break. Yes. How much time you want? 5 minutes, David?
Or let's say so from in my computer it's well, 2:37, 3:37 there, I guess. Let's make it like more or less 10 minutes. Let's say at 2:50, 3:50 for you, more or less.
Okay. 2:50, so small coffee break. You
Yeah,
could all go for a
that's
sandwich.
What I
do. And 3:50, yes, and for David 2:50. We will seek David again. I will not. So you could stay here, yes. Yes. I will not turn off or leave meeting. I will just pause translation.
Okay, and okay, here it is. Can you see my screen?
Yes.
Oh, okay. Well, so welcome back, everyone. We spent that first hour basically providing an introduction to the BioArt project, in which, in the context of which this presentation was prepared, and then talking about biometric recognition in general and about ECG-based biometric recognition in particular. Now we are going to see, to provide a detailed description of 2 approaches that were programmed by two students of mine, two bachelor students of mine. So the first one is a fiducial approach. It was programmed by Ana Garcinuño in December 2019. I can give you the document for her project if you are interested, but it's in Spanish. Okay, so I think probably it's not very useful for most of you, but if someone is interested, I have no problem in in sending it. Actually, it should be available through our university's library. It should be freely available. Well, in any case, this is what we are doing. Okay, we took not a very recent approach, because it was the approach that I mentioned before from Israel, combined with the one of Wong. So essentially, we took the 15 time features that Israel selected long time, 15 years ago, and then we extended it with the amplitude features that were proposed by Wang 3 years later. It is a classical signal processing and machine learning approach. Okay, it's not using deep learning or any other more modern and state-of-the-art machine learning methods, but still you will see that it provides very good results. Of course, the idea for selecting this method also was that was based on the background of our students. Our students are electrical engineering students. They have one course on linear signals and systems, one course on digital signal processing, and one course on statistics and probability and statistics, essentially. Okay, but they do not have any course on machine learning, and they do not have any course on statistical signal processing. Okay, so here they were already implementing things which go beyond what they have learned in their BSc courses. But still, those two students from the two projects that I'm going to show you now did a very good work, and they were able to implement the whole block diagram. Here you will see a very simplified version, and then they were able to obtain very good results. So in short, what this approach is doing, we start from a signals database. We intended to record our own database this year, but I had a student who was going to do that, but with COVID, it has not been possible. But in general, there are many databases, many ECG databases publicly available through the internet. Okay, so we start with a publicly available database. We extract those signals, okay, or we download those signals, and from that, the first thing we are always going to do is pre-processing. Pre-processing, in this case, it's a fiducial point extraction, but it also includes denoising. It also includes applying some filtering techniques to remove noise and interferences. In this case, the method, the algorithm that is used to detect the QRS complexes already includes filters to remove that noise and interference. Okay, so we did not need to use additional filters, but they are already included in the fiducial point extraction. Then, once we extract the fiducial points here, we have to perform dimensionality reduction. Why? Well, because fiducial points and features are typically based on physiologically meaningful quantities. Like, for instance, as I said before, the length of the P waveform, the difference in amplitude between the R and the S peaks, or the length of the T waveforms. Of course, that makes sense from a physiological point of view, and it would make a lot of sense if we are trying to detect some pathology, because it is well known that the shape or the duration of these waveforms is related to certain cardiac pathologies. And this is being used nowadays in cardiology, okay? But we are not interested in that. We are interested in identifying individuals. And the characteristics which are physiologically relevant may not be the best ones to identify individuals, on the one hand. And on the other hand, these features are typically highly correlated. So we do not want to keep those 21 features that we have extracted. We want to obtain a reduced set of features that, even though they do not make sense from a physiological or from a cardiological point of view, they are going to give us the best possible performance for our multi-class classifier. Okay. Actually, this is a mistake. Because this is what we did in the non-fiducial approach. Okay, not in the fiducial approach. Here, what we did was applying a method which is known as Wilks discriminant analysis, which allows us to select the most relevant features for our analysis. Okay, I will correct this before sending the slides to Galina. Okay. And then we applied a classifier. There are many classifiers. In this work, we applied the simplest possible classifier, which is k nearest neighbors, and it worked quite well. It worked really well, actually. Okay. So the goal of this is to show you how, as a student, you can implement a whole block, a whole biometric recognition block with the knowledge that you have from your degree. First, and you can test it on real signals, and also that it is not always necessary to apply the latest and the most complicated methods in machine learning and signal processing. Sometimes simple approaches, properly selected or properly combined, can lead to very good performance. Okay, and this is also important because if you're going to implement it in powerful computer, then you don't care so much about the computational power and about the amount of memory that you may need to store your model. But if you are going to implement this in a portable device, computational cost and storage is a very important factor. Okay. So let's start first with the PTB database. The PTB database is a clinical database which was recorded in Germany. It contains 290 subjects. Of course, since it is a clinical database, this means that most of the subjects, most of the individuals are patients with pathologies. So you can see that out of these 290 subjects, 238 have some cardiac pathologies. Okay, and we have only the control group is rather small. We only have 52 completely healthy patients. So this is clearly not the situation that we are going to find in real world. If we want to implement some ECG based biometric recognition system, because then it's probably going to be the other way around. Okay, 80-90% of the people are going to be healthy, and then the other 10 or 20% are going to be patients with pathologies. But still, this is a good test because it's going to make the problem more challenging, because patients with pathologies are going to have abnormal ECGs. Okay, and in these ECGs, it's going to be quite challenging to extract the fiducial points, and the shapes are not going to be adjusted to the typical shape of the PQRST waveforms that I showed you before. So it's a good database to test ECG-based approaches, and it has been widely used by many people. It's actually it's probably the most widely used database to test ECG-based biometric approaches. Okay. Apart from having 290 subjects, another interesting thing is that it has 549 records. So this means we have almost 2 records per subject. This is not exact, so for some subjects we just have 1 record, and for some other subjects we have 7 or 8 records. Okay, but this means we have several sessions. We have recordings for one subject in several sessions, which is also a very interesting thing to do. Okay. Well, we have in cardiology, typically we record at least 12 standard leads. These leads are called 1 to 3. Then we have these are called the augmented limbs, and these V1 to V6 are called the precordial leads, and these are the leads which are obtained closer to the heart, and these are the ones which have the cleanest signals and the highest amplitude. Apart from those, in some cases, we also acquire what are called the Frank lead ECGs, which can be obtained actually from the other 12 standard leads. I think there is a question in the chat. Oh, okay. As far, yeah, I think it's, let me see. Yeah, it said below. Look, we just have to go 2 lines below. The duration of each register is around 2 minutes. Okay. But
it was the second question, but there was the first one. Okay, I suppose it was from the previous slide. Yes. Why use namely PCA? Yes. What about? Can you see it? Please look in the chat.
Yeah, I'm seeing. Why we use PCA? Okay, that's also a good question. I don't know, MD. What is MD? I don't know what MD corresponds to. And correspondence analysis, I don't know if he refers to maybe canonical correlation analysis or something like that. So PCA is a classical technique to reduce dimensionality. There is a slide about PCA, multidimensional analysis. Okay. Yes, there are many techniques which could be used. Okay. So ICA, independent component analysis, is usually we use that normally to separate signals which are mixed together. But in this case, we don't have signals; we have features. Okay, and actually, our goal or what we want to have is detection, or we know it is possible, okay, to perform detection from a single beat. From a single heartbeat, we can perform identification of a person. So in this case, we have 21 features, for instance. So it does not make a lot of sense to apply ICA, okay? Because we are not talking about signals. We are talking about features. We are applying PCA on the features, okay? So we could apply other methods. I'm not saying that this is not possible, but PCA works rather well, and it is a standard approach. So we did not test other more sophisticated or non-linear approaches. Okay, we just tested this is Wilks dimensionality reduction. This Wilks method, and we also tested PCA. We did not test others, but of course there are other possibilities. ICA, I don't think it is applicable in this case, at least not as we did it. Okay, if you could try to apply that to the signal before extracting the feature, that could make sense. But applying that to the features, I don't think that makes sense. But many approaches could be used. Okay. Oh, okay. Thanks to you for asking. Well, that's what I was saying. So in any case, the duration of the signals is around 2 minutes. There are this PTB database. I have to say it. You have it here. It was downloaded from Physionet. Physionet is the main repository, the main online repository of biomedical signals. It has thousands of biomedical signals, all types of biomedical signals. Okay, it has ECG, EEG, multimodal data sets where they measure respiration, blood pressure, all kind of signals all kind of biomedical signals that you can think of. Probably there is some database in Physionet that can be downloaded for free. Okay, so if you have any kind of problem, not just biometric identification, if you're working on biomedical signal processing or bioinformatics approaches, there are many chances that you will find some database that you can use in Physionet. So it's it should be your first stop if you are doing biomedical signal processing or machine learning approaches with biomedical signals. Okay. Well, so this database was downloaded from VisiNet. The length of each register is around 2 minutes. There are other databases that have longer signals. Okay, like the MIT BIH database has signals which are 30 minutes long. There are other signals which are recorded on patients with sleep disorders who are monitored throughout the whole night. So this can be like 8 or 10 hours long. But the problem with those databases is that the number of subjects is much smaller. Okay, this has a large enough number of subjects, and 2 minutes is more than enough, because as I said before, with the approaches that we have implemented, with this one in particular, we should be able to identify the person with a single heartbeat. Okay, the other one that I'm going to show you needs a bit more time. It will need around 5 to 10 heartbeats to identify one person. On the other hand, I will show you that it works better. It's more robust. Okay, but in this case, just a single heartbeat should be enough. Well, this is a high-quality signal with large resolution, 16 bits, almost no noise and interferences because it had been recorded in a clinical context, and then. For starters, we always worked with lead V4. This is one of the precordial leads. It's one of the strongest signals because we wanted to test whether this approach was working well or not. And we started working with the 52 healthy patients. But in the end, we applied the approach to all the patients. Okay, so here you can see. I'm not going to get into all the details about this, but I want to show you the different stages of the approach that my student implemented. Okay, so we had the PTB database. We extract the ECG. We select one of the 15 channels. Okay, because we wanted to have a single channel approach. In practice, if we are going to use this, we are going to work with one signal. We are not going to ask the person to put all the electrodes and to record the 15 signals. So we have the ECG, and now we want to extract the fiducial points. For the fiducial points, we cannot follow a single approach because there are some signals which are some parts of the signals, which are heavily peaked. So we have large peaks, and there are other signals which are much smoother. So it is not appropriate to use the same kind of processing for all the signals. So what we have is like a battery of 3 filters. Okay, one is a low pass filter. Another one is a derivative, a differentiation filter, and another one is a bandpass filter. Okay, so for the derivative filter, you can guess this is not the frequency response. This is just the range of frequencies where the derivative is operating. Okay, so for the first signal, we apply a bandpass filter. So we take the part from 1 Hz to 15 Hz. For the differentiator, we apply a 4th order differentiator, and for the last signal, we apply a 3rd order Butterworth low pass filter. So this is the one that will be used for the P and Q waveforms. This this is another mistake. This is P and T waveforms. Okay, this is the P and T waveforms, the smooth ones, and these will be used for the QRS complex, which has the signals which are changing faster and have frequency contents which go a bit beyond 12 Hz. As you can see in biomedical signals in general, frequency content is quite low. Okay, if you are used to working with other signals like communication signals, the frequencies here are very, very small in comparison. So the first thing we do is we apply the Pan-Tompkins algorithm. The Pan-Tompkins algorithm is a classical method to detect the R peaks. It's quite old. It's 1985, but it still works very well. So the Pan-Tompkins method essentially takes the raw signal. So, well, first maybe I should say that we took the signals from all the channels. My student applied, because I said we selected V4. Okay, you will see, but you will see that that's the channel where everything works very well. But she tried she also made the study of trying to apply the method to all the channels. Okay, she performed the fiducial point extraction and the segmentation for all the channels to see which ones worked better than others. Well, in any case, we select one channel, let's say V4, as we said before. We apply the Pan-Tompkins method, okay? So the Pan-Tompkins method takes the raw ECG signal, perform a bandpass filtering, because the Pan-Tompkins method is only interested in the QRS complex. So we want to remove high-frequency noise and low-frequency components, which correspond to the P and the T waveforms. Then we perform a derivative, because peaks, we are interested in detecting peaks. And actually, we are interested in detecting the R peak. And the R peak corresponds to the largest slope in the signal. So that's going to be better identified with the derivative. Then, after performing the derivative, we perform the squaring of the signal, so that we get rid of problems associated to inverted polarity. Okay, we just the goal in the end is to be able to work with a single threshold. And then we finally end up performing an average, because here, if you see, we have many peaks. The signal is squared, but we still have many peaks. Okay, so we perform an integration and an averaging of the signal with a length of this moving integration, which is roughly equal to the expected length of the QRS complex. So we end up with a very smooth and very clear signal. And then all we have to do is to select a threshold. Okay, so this is we have like we keep tracking the average amplitude of the last peaks. This red line is the average amplitude of the last detected peaks, and we set the threshold to be a fraction of that selected of that average amplitude of the peaks. Okay, so that's how the Pan-Tompkins works. It has some other features, like, for instance, if it does not detect a peak in a large time interval, then it goes back and it decreases the threshold, because of course we know that we should have at least 1 bit per second, more or less. Okay, so if it waits some time, maybe 1.5 seconds, and if it has not detected a single peak in 1.5 seconds, it goes back, lowers the threshold, and searches again. But well, those details are not very important for this talk. Okay. Well, so after selecting the R peak, so the R peak is this one. After selecting the R peak, we have to go back and forward to find the S and the Q. Sorry, let's look here, because these samples are exchanged, to find the Q and the S peaks. How do we find those peaks? Very easy. We have the derivative. We have performed the derivative of the signal to find the R peaks. This Q and this S correspond to zeros in the derivative. So the Q peak is the first zero crossing before the R peak. The S peak is the first zero crossing after the R peak. Okay, and then the P and the T waveforms are found using this low-pass filter signal. This low-pass filter signal is going to remove high-frequency noise and these high-frequency peaks. So we are only going to get these smooth signals. Okay, and then from those signals, we are going to be able to extract this peak and the beginning and the end of the P and the T waveforms. Okay, as you can see here, what we have, well, actually for this we used also a standard approach that we had to or my student had to program. In any case, what you can see here is two examples, okay, from two subjects, subject 24 and subject 112. It's channel 10, which corresponds to V4, as we said, and you can see, for instance, that these are all the heartbeats We perform a bit-by-bit segmentation of the signals. You can see all the heartbeats. And you can see, hopefully, here you can see how this or why this works. You can see these two signals. They look a bit similar, but you can also clearly see differences. The length of the P waveform for this patient is not the same as for this one. The height, in this case, the height of the QRS peaks is quite similar, but there are small differences that we are going to be able to exploit in our classifier to identify one person from the other. And also you can see that heartbeats are quite regular, okay? They repeat themselves quite a lot. Okay, this is a healthy patient. We had a patient with pathologies, things are not so easy. There would be differences, okay? But for a healthy patient, over a 2-minute interval, heartbeats are quite regular, both in amplitude and in duration. And if you can see here some change, some uncertainty in the beginning or in the location of the peak for the waveform, that's not only due to the fact that heartbeats change from one sample to the other, but also on the difficulty of finding the beginning and the end of these waveforms. It's very difficult to find the exact beginning and the end. You can see it here. There is hardly any change in the waveforms, and then there is some uncertainty in the end of the P waveform. You can see it's so smooth that it's very difficult to decide exactly where that waveform finishes. And that's one of the problems that fiducial approaches have for ECG-based recognition. Okay, well, in any case, now we have all these samples. We have the beginning of the P waveform, we have the end of the P waveform, we have the peak of the P waveform, we have the QRS peaks, we have the beginning and end and the peak of the T waveform. So we can use all that information to extract features which are based both on the time and on the amplitude. Here I put the 15 features that we have in the time domain. And as you can see, essentially it is the times, the elapsed time, the duration of the different waveforms or the different intervals that we have in the PQRST waves. Okay? Well, as I said before, now we have these 15 waves, these 15 features, sorry, which are based on time, and we have other 6 features which are based on the amplitude. We could train a classifier on these features, but I can already tell you that this is not going to be the best idea, okay? It's going to work, it works, but we're not going to get the best possible performance because there is a lot of correlation between those features, and actually this correlation can confuse the classifier. It's not a good idea. In general, it's not a good idea to use the initial features for your classification, especially if these features have been designed or have been extracted based on some kind of physiological criteria. Okay, because that's probably not the best option for the classifier. So what we did is we used this stepwise procedure. We could also apply PCA, and actually in the other approach we applied PCA, but in this case we used a different approach because we were interested in keeping the original features. Okay, again, that's usually not the best criterion for classification, but if you want to have interpretability, if you want to know which features really are useful for your classification, then it might be interesting to use this approach. Because when you apply PCA or other nonlinear feature reduction approach, then you lose sight of you lose interpretability of those features. Okay, in the end, your feature is going to be in PCA, for instance, your selected feature is going to be a linear combination of other features, and then you can identify, you can perform factor analysis, and you can identify which factors, which features contribute more, but it's not the picture is not going to be so clear. So here, what we did is, I don't want to go through the detail. I don't think it makes sense here, but essentially, what we do is we compute this Wilks lambda statistic. So here, well, this Wilks lambda statistics is the ratio of two things. One is the within class sum of squares matrix, and the other is the total sum of squares matrix. Okay, so this is going to be related to the variance of the features within a single class. So within a single, here a class is a subject, is an individual that we want to identify. Okay, so if you remember, we had 52 healthy patients. So we have, sorry, I'm making a mistake. This is within class. Here the classes are the features. Okay, so we have 15 features, and we want to determine which features perform better. So in the end, we want to have features for which the within class difference, the within class squared difference is as small as possible. Okay, with respect to the total difference. So we compute this, we select the, I don't know, if we have 15 features, we can rank those features, and we select the 3, 4, 5, 6 features which have a smaller value of this Wilks lambda. Okay. And well, actually we have like two criteria. We can select a number of features. We can say, okay, we are going to take 6 out of these 15 features, or we can select a significance level. We set it to that's a typical value, okay, to 0.05, and then we select those features for which the significance level, okay, the significance level meaning that these additional features are still statistically significant, okay. So we keep selecting features until the significance level drops below this threshold, okay. That's Wilks lambda. The other approach is PCA. Okay, so PCA is just a linear feature extraction or dimensionality reduction approach. Again, I don't know if it makes a lot of sense here to get into details, but essentially we perform. So this is the feature matrix. Okay, so we have the features for all the patients, all the subjects, and all the heartbeats that we have extracted. So we perform the correlation, well, the covariance actually, the covariance of the features, and we normalize that by dividing by the variance of each feature. Okay. And then what we are going to select, we perform an eigen decomposition of this correlation matrix, and we select the m highest eigenvalues. Okay, so this means it's like if we have 15 features and we select just 4, we are going to select 4 eigenfeatures which have the largest covariance. Okay. So, or which correspond to the largest eigenvalues. And these features, the problem with PCA works quite well, but the problem with PCA is that these features are not going to be associated to any of the original features. As I said before, they are going to be a linear combination of the existing features. So if we have 15 features, the first one selected could be 0.01 the first one, 0.0 plus 0.02 the second feature, plus 0.6 the third feature. So we could have some features which are which have larger weights than others, but it's not going to select a single feature. So interpretation of which characteristics, which features are more relevant for identification is going to be complicated. Okay. The previous one, the Wilks, the stepwise Wilks lambda procedure, selected features one by one, but features from the original one. Well, I don't know if it makes sense to get into more details. in any case, so we wanted to also check which methods worked better. So from the work of this student, now I'm talking about one study that we did like 1 year ago, and that we submitted to a conference with a PhD student. So, but it's the same approach, okay? It's the same. It's the same method that my bachelor student programmed, and we wanted to check what happened with the different classifiers. I told you that my student programmed the k-nearest network, but we wanted to compare with other more sophisticated approaches. Okay, so k-nearest neighbors. There is one slide afterwards. Essentially, we have one sample, and we compare it to the k closest samples, and we label that sample based on the labels of those k closest samples. Okay. Support vector machines, linear discriminant analysis, or quadratic discriminant analysis are state-of-the-art machine learning classification approaches, especially SVMs. I'm not going to go through that. Let me just explain you what k-nearest neighbors is. This is actually a picture that my student did. Okay. So let's imagine that we have two class classifiers. So we train our classifier to distinguish dogs from koalas. Okay, and these are the samples. These koalas and these dogs are the samples that we have used to train the classifier, and they are plotted in feature space. So in this case, this feature space is two-dimensional, which means we have two features. Okay, so we have one feature here in the x-axis and another feature here in the y-axis. Okay, so we plot the samples, the samples that we have in the training set according to those two features. And we say, well, koalas are. We can see clearly that these two sets are properly separated. Okay, so koalas are on the left side, dogs are on the right side. So now we get a new sample, this triangle here, and we want to know whether it is a dog or a koala. Well, with k-nearest neighbors, the approach taken by k-nearest neighbors is simply to look for the k samples which are closest to the new one. So in this case, for instance, if we select k equal to 3, then we would have these three samples. So we have two dogs and one koala. So then k-nearest neighbors performs majority voting, and it says, okay, so we have the out of the three closest samples, usually we always take an odd number. Out of the three closest samples, we have two dogs and one koala. We have more dogs than koala, so this must be a dog. Of course, here you can also see the danger of k-nearest neighbors. This value of k has to be chosen properly, because if we choose k equal to 5 instead of 3, we have this circle, and then here we have 3 koalas and 2 dogs. So then we would say, okay, then this new sample must be a koala. Of course, here I took a sample which is just in the limit between the two classes. If I had taken the sample here, then we would clearly get a koala, regardless of the value of k. If we take a sample here, we would clearly get a dog, regardless of the value of k. Okay, but in the limit, it can be difficult to decide from koala to dog using the k-nearest neighbors, as you can see here. Okay, the choice of the value of k is critical. It works reasonably well. This approach, it's very simple, and it works reasonably well in many problems. But the choice of the value of k is critical. And this is what my student got. Okay. So she tried she changed. Here we have the percentage of samples that we have from the training. So first she extracted all the heartbeats from all the subjects, and we used a certain percentage of those samples to train our model. Okay, so we tested from 70 to 90%, and we also tested the number of nearest neighbors. So two conclusions we got is that the training percentage does not have a big influence. Okay, you get that here. You can see that here we get the best results, but this is 85.1% versus 84.3%. So this is just a 0.8% increase by increasing by 20% the training percentage. So it's not a big difference. Okay, and here it's the same. You go from almost 95% to 95.4% by increasing by 20% the percentage of the training set. That's one of the things we saw. Also, we saw that as we increase the number of neighbors, things get worse. Okay, probably because of these samples which are close to the limit. So we saw that actually in this case, the best performance was obtained if we took the nearest neighbor. So if we take here the nearest neighbor, we'll say, okay, this is the dog. And that provided very good results. So those were two conclusions. And the last conclusion, we knew that amplitude attributes would improve the performance because we could see that from the literature, but we did not expect it to improve by so much. So you can see here that by using only time attributes, we get around 85% recognition. Okay, so this means out of every 100 subjects who enter the systems, 85 are properly recognized. But when we use also amplitude attributes, we go from 85% to 95%. So it's a 10% improvement by just adding those 6 amplitude attributes to the 15 time attributes that we had. So that's a large improvement, which was not expected at the beginning. Yeah, I'm afraid this part is a bit more technical. I've tried not to get into details, but well, I cannot help providing some details. Okay. In any case, I hope you saw the general framework and the general approach that we took. Okay, and I hope I also convinced you that ECG-based recognition can work well. I have to say that these results are with the whole data set. Okay, these results are not just for the healthy patients, are for the 549 signals from the 290 people. So they are reasonably good results. Okay, still 95% recognition is not enough if we have a large population, because this means that we will fail too many times. Okay, so at the same time, I had another student who was working on non-fiducial biometry. This is his name was Gerardo Aguirre. He also did his work in 2019, and you can see here like the whole block diagram of his approach. So we took the signals from Physionet. We took the same database, PTB. We performed some pre-processing, some filtering. We performed, as before, we performed segmentation, okay? But in this case, the segmentation did not rely on fiducial points, okay? So it did not rely on detecting DR waveforms. We just took 5 seconds of the signal. From the start to 5 seconds, the next 5 seconds, and so on, regardless of where the R peaks were. We did not extract any peaks. Then we performed autocorrelation, and we tested 3 different approaches. Okay, we tested using a discrete cosine transform. We will talk about that now. So this is essentially these approaches were used for dimensionality reduction. Okay, so the autocorrelation approach is going to provide the features that we need for classification, but of course here we are going to end up with a really large number of features. Okay, so many more than the ones we had before. So we need to perform some dimensionality reduction. So in the first case, we use the DCT, the discrete cosine transform. For the second case, we use the linear discriminant analysis. This was recommended in the literature but we found that this did not work too well because it had numerical problems. So we decided to test PCA plus LDA, and this was the killing block diagram. This worked extremely well. So we got more than 99% recognition. Okay. So essentially, as I said, we used the same database. We extracted the signal. We performed a fourth ordered bandpass Butterworth filter to remove noise and artifacts. If you remember, that was the same one we used before, the fiducial point extraction. And after removing the noise, we segmented the signals in blocks of 5 seconds. But again, it's important to emphasize that this was done without any consideration about where the heartbeats are or where the R peaks are. Okay, we could have a signal which is split in the middle of a QRS complex, or we could have or in the middle of a P waveform, or in the middle of a T waveform. We did not care about that, because caring about that means performing some approach to detect those peaks. And we have already seen that this can be, well, this is time consuming, of course, and it can also be, have problems for some patients, for noisy signals, or for patients who have pathologies. We may have trouble finding those blocks. Okay, so we just segment that signal, taking blocks of 5 seconds from the beginning of the signal. Okay, so from those blocks we perform autocorrelation, and here you have a picture of the autocorrelation. You have it expanded here. So this is this first one is the one that we had in the previous slide. So what is autocorrelation? It is essentially the expected value of the signal at one instant times the signal at another time lag. And here we are showing the value of this correlation with respect to the time lag. Okay. So you can see that here we move from 0 time lag, where we have the peak, the highest value of the autocorrelation, up to 800 samples. And here we can see two things. First, these are two subjects, two patients. First, their autocorrelation patterns are very, very different. So this convinces us that we can use autocorrelation as a feature to distinguish between two people, between two subjects. Okay, because the autocorrelation of this person is very different from the autocorrelation of this second person. So this is a characteristic, a unique feature of the people. And why is it like that? Well, essentially because the autocorrelation is going to capture the similarities and the differences as time goes by in the waveforms that appear in the ECG. And as we said before, the width and the amplitudes, the length of the duration of those waveforms is a feature which is unique of each patient. So of course, all the autocorrelations will have a kind of similar shape, right? With a peak here and then some oscillations. But these oscillations, you can see that they are wildly different from this subject to this subject. Here the oscillations are much larger. Here they are much smoother. Okay, and also the width of those oscillations is much is very different. Okay, so that's something we can see. This autocorrelation is able to characterize people. This autocorrelation of the ECG signal. And the second thing that we can see, this first conclusion is related to the large intersubject variability, which is something good, which is something we want. We want to have very different autocorrelation for different people. The second part, the large here, the large intrasubject variability is something that we do not want. And this is something that we see here. Here we have plotted the autocorrelation for all the segments of 22 segments, in this case, of the first subject. And here we have plotted the autocorrelation of the 22 segments from subject 2. And you can see that the first part is quite stable. It's the same for all the 5 second segments, but the last part, there are changes. there are differences. And here it's the same. This is even, these changes are even larger. So that's another conclusion that we can use. This part cannot be used for classification. This is useless because there are going to be so many differences that the only thing that we are going to get is confusion. Okay, even though we can see peaks, the peaks are not in the same location, the amplitudes are not the same, so this part is useless. But if we stick to the first part, maybe 200 or up to 300 samples, or milliseconds, sorry, this is actually milliseconds, we can distinguish clearly from one subject to the other, and the signal remains quite stable from one segment to the other. So that's essentially what we do. Okay. However, even if we take, let's say, 300 milliseconds, since our sampling rate is 1 millisecond, this means we will have 300 samples. 300 samples means 300 features, and we do not want to have classifiers with 300 features. Okay, so what we do is we perform an approach to have dimensionality reduction, and the approach that was suggested in the papers that we started working with was the discrete cosine transform. In case you don't know, the discrete cosine transform is similar to the discrete Fourier transform, except for the fact that instead of complex exponentials, it uses cosines. So it is easier to compute because we don't have complex numbers, we just have real numbers, and it has a very nice property, which is energy compaction. It is well known that the discrete cosine transform tends to compress all the energy of the signal in a few coefficients, which are the first few coefficients. So here you can see, here actually we took a block of length 500, okay? And you can see that after 40 coefficients, the density is almost zero. So this means that instead of getting 500 coefficients, 500 features, we can have just 40 features. And here you can see the reconstruction using different numbers of coefficients. For instance, here we use 21 coefficients, so we use the first 21 coefficients, and you can see in blue the original autocorrelation, and in red the reconstructed autocorrelation. You can see that the result is not too good. There are oscillations and there are lots of differences. But when we use 27 instead of 21 coefficients, the result is already quite good. And when we use 35 coefficients, okay, the first 35 coefficients here, the reconstructed autocorrelation is almost the same as the original one. Okay. By the way, this has nothing to do with the lecture, but the discrete cosine transform is used in image compression. Okay, the JPEG standard is or other image compression standards use the discrete cosine transform just because of this property. Okay, because we can compress a signal or an image. An image is a type of signal. We can compress it using just a few coefficients, and the idea is the same. We are going to perform the discrete cosine transform, the two-dimensional, in this case, discrete cosine transform of the signal, and then instead of using all the coefficients of this transform, we're just going to use a subset a few coefficients. Okay, the first few coefficients. Depending on the quality that we want, in the JPEG, in JPEG, for instance, depending on the quality that we want, we will use more or less coefficients. If we want a lot of compression, then maybe we just use a few coefficients, and then of course the reconstruction of the image will not be so good. If we want higher quality, then we will use more coefficients that capture maybe 90% or 99% of the energy of the signal, and then the reconstruction will be almost indistinguishable from the original signal on first sight. Okay. Well, that was, as I said, the first approach we used to test for dimensionality reduction. Second approach that we used was LDA, but that did not work too well. So we ended up using PCA plus LDA. plus linear discriminant analysis. Okay, so well, here you have like a visual representation of PCA plus LDA. So what PCA does, basically, we have this cloud of samples of in feature space. Okay, so here we have two features, X1 and X2. And PCA, what it does is, imagine that we have an ellipse, okay, with all the samples. So PCA essentially tries to find the main axis of this ellipse. Okay, it tries to find the main directions along which the samples are aligned in feature space. So usually this is used to select, okay, if I just want the main direction, if I want to reduce my dimensionality from 2 to 1, I will take the main direction, the main axis of the ellipse, and I will get this. Okay, this will be the only feature that I'm going to use. But here we didn't use PCA like that, because we used PCA, but we kept all the features. So the only thing we did is we used PCA to rotate this cloud of features, so that instead of working with something like that, we had this problem. Here we have two clouds, okay? One cloud corresponds to one class, the other cloud corresponds to another class. And then LDA, linear discriminant analysis, performs a projection on a lower dimensionality space so that the separation between the two classes is maximized. So here you can see two examples. Very simple example, okay? Two features. You can see two examples of bad projection. If we project these two clouds corresponding to the two classes on this axis, we have a very bad projection because the distribution of the two samples is the same. If we project it on this axis, this is a very good projection because the distribution of the two classes can be clearly distinguished. So we can put a threshold here, and just by putting a threshold here, we would be able to distinguish samples from the two classes. I think there was oh, okay. Galina saying that I just have 5 minutes. Okay. Okay, I'm already finishing this non-fiducial because we just have the results. So this is the true positive rate. Okay, this is the number of positively recognized samples. So you can see that using autocorrelation plus DCT, we get with 75% of training, okay, we get 99.1% success using just k-nearest neighbors with one neighbor, okay, because again, we saw that by increasing the number of neighbors, the performance decreased. And if we use PCA plus LDA, the performance was slightly better. Not much better, but it was a bit better. So 99.1 versus 99.3. And that's it. That's all I wanted to tell you in detail, because I wanted to describe these two methods in detail so that you could see things that you can do by yourselves as your final year project, or with the knowledge that you will gain at the end of your bachelor degrees or your master degrees. You could perform this or even more sophisticated approaches. Just to finish very briefly, recently in the last 3, 4, 5 years, people have started applying deep neural networks to this approach. Deep neural networks are the state of the art in machine learning, and in particular, deep convolutional neural networks are widely used in applications like image recognition. Okay, so here we do not have an image. We have an electrocardiogram, which is a signal that changes with time. Can we apply deep neural network approaches? Yes, we can apply them by performing or by computing some kind of time frequency representation. Okay, so we can use, like for instance, we can compute the Fourier transform of the signal in windows, in several windows, and using those windows we can concatenate the Fourier transform for those windows, and then we get an image. That image can be used to train some convolutional neural network. And from that, from the output of this network, we can classify different individuals. So in the next slides, what you have is the different ways that that people have used to construct these images, and then the different networks. It's like an overview of different neural networks that people have used for this ECG based biometric recognition. I'm not going to get into detail here because this is not a machine learning course or a deep learning course. But you have here, you will have these slides. Okay. Let me just go to the last slide for the deep learning, where you can see the performance. Okay, and you can see here the performance of the different methods used to construct the images, and here the performance for the different networks. You can see that in the best case we get 99 percentage. Okay, so it's good percentage. It's good performance. In the best case, it attains 99.77% accuracy. But if you remember, using simpler approaches, we already got 99.28% accuracy. Okay, so deep learning is great, but it also needs a lot of data to train the network properly, and more computational more computational power to train the network. Sometimes maybe we don't need so much. Sometimes using more classical machine signal processing and machine learning approaches with tools that you may have seen in your degree, you can already attain a very good result. And well, that's almost it. Just 1 minute to finish. As I said, we can develop with the knowledge that you gain in your degrees. You can develop fiducial and non-fiducial methods to perform ECG-based recognition. In both cases, we attain, I don't know, maybe excellent is too much. We attain very good performance, okay, above 95% performance, and in the case of non-fiducial methods, sorry, more than 99% performance. PCA can be used to reduce dimensionality and also to increase the stability of LDA, okay, and very, very simple classification approach, KNN with K equal to 1, provides a very good classification with a ridiculous computational cost, with a very low computational cost. Future lines, many. Okay, although people have been working for 20 years in ECG-based biometric recognition, there are still many unanswered questions in this field. And if we go to the global field of biometric recognition, there are even more open issues. Okay, so one thing that I already mentioned is test this approach along larger periods of time. We perform the validation using a clinical database with a very good quality, but the signals that we will have in real life, this is going to be applied in practice, are going to be of lower quality. So we need to have databases with lower quality. Actually, very recently this year, some Portuguese guys who are working on this, they released a database of signals with lower quality, so that we will probably be using next year to validate our approaches. And of course, we need to explore. Well, deep learning is being applied everywhere, and advanced machine learning methods are being applied everywhere. So we will need to explore these more in detail, to see how it applies and which are the limits for these approaches. So that's all from my side. I hope you enjoyed the course. I hope I could convince you that this is an interesting area to work in. And I hope I also encouraged you to work in this area of biomedical or biometric recognition and biomedical signal processing. Just let me remind you that we have a mobility agreement with Ukraine. So if any of you is interested in visiting us in Madrid, you are very welcome to come.